Hi everyone, my name is Peiyu, a PhD student from the University of Western Australia. It's my honor to talk about our recent work regulating model reliance on non-robust features by smoothing input marginal density. Nowadays, deep learning has achieved great success in many real-world applications, including classification, object detection, and segmentation. The lack of transparency hinders the application of deep models in high-stakes applications such as transportation, finance, and criminal justice. To provide an understanding of black box models, different explaining tools are developed to explain decision-making process of the models. Although there are different types of explaining tools, there is still a gap between model explanations and model robustness. In this work, we investigate how to incorporate explaining tools into the process of enhancing model robustness. And before discussing the regularization term for model robustness, we first define robust features by attributions as definition 1. In this definition, we define input features of robust feature if features can consistently contribute to the model prediction. Based on this definition, we further identify and summarize remark 1 that robust features are condition invariant, which means robust features can consistently contribute to model prediction despite the changes to the input. Motivated by the identified properties of robust features, we start our derivation from a joint probability density function over input as definition 1. And by applying Bayes' rule, the marginal density can be expressed as equation 2. And then we identify the relation between the gradients of input marginal density and the smoothness of output losses as remark 2. In the light of remark 2, we derive our regularization term that encourage a small gradient of the marginal density, facilitating the use of robust features. However, the partition function within the density function is intractable. We instead compute the gradients with respect to log density. Thus, we derive our regularization term as the p-norm of the log gradients of density as defined in equation 3. However, the regularization term includes an exponential operation which will cause numerical instability. To overcome this problem, we incorporate the softmax function into the gradient computation. We conduct experiments to compare different implementation approaches. These results show that our approach can lead to a stable and efficient implementation. In addition, we further review the limited robustness in input gradients regularization. And input gradients regularization computes the L2 norm of input gradients as the regularization term, which is a widely used baseline robust regularization. However, we show that input gradients regularization can be regarded as smoothing the joint and condition density of input. Thus, it is defined under the assumption of a specific label, compromising its ability to resist the class-specific non-robust features. In our experiments, we first evaluate our regularization on block MNIST dataset. The sample of a block MNIST consists of an uninformative non-block features and informative number features. The non-block features are randomly placed at the top or the bottom of the image. The standard trained model is found to incorrectly rely on non-robust non-block features, evidenced by the attribution map, and this phenomenon is termed feature leakage. We employ integrated gradients to measure the leakage attribution to the non-block region. And experimental results show that our method can also effectively express the leakage problem. However, input gradients regularization fails to address this problem due to its limited robustness. And similarly, on the celebrated datasets due to the imbalanced training samples, the model tends to rely on spurious features of gender to classify the hair color. Our experiments on both celebrity and vertebral datasets show that our method can effectively mitigate this spurious correlation problem. And moreover, our method is evaluated to show general robustness against the perturbation on input pixel gradients and input density. The results highlight that our methods are robust against two different perturbations. Thank you for listening.